Okay, Newton's method. Newton's method is a way to approximate like the square root of 5, or another way to say it, we're going to find the root or the x-intercept of some like y equals x cubed minus 2. Again, pretend you don't have a graphing calculator and you're going old school here. How would you use calculus in order to find that? So let's look at the square root of 5, because what we're going to do is we're going to claim that if we want to find the square root of 5, that's the equivalent thing of saying, let's try to find x squared minus 5's x-intercepts. Well, if I can find this x-intercept, I know it's at the square root of 5. And so, wonder what that would look like. Well, on a graph, if we drew this, this is going to look something like, right, our nice, easy parabola. And you're like, oh man, the square root of 5, that root, it's right there. How would you find it? Okay, let's just guess something. Let's guess. And I'm going to guess 3. I know it's not 3. I know 3 squared minus 5 isn't 0, but let's guess 3, and that would be right there. And here's Newton's method. Newton's method says that if we want to find the 0, or the x-intercept, we can just make a guess. And then with that guess, what can we do with calculus? We can find the equation of the tangent line. And so we find the equation of the tangent line. And then you know what we can do with lines? Well, we can find the roots of lines real easy. So you see right there where that line crosses the x-axis? That's going to give me a new point. And guess what I'm going to do? I'm going to do another iteration. Another iteration means I do that whole process again. So I use that new point. And I use that point on the curve. And you know what I do? I find the tangent line at that point. I know you can't really see, but you could look this up, maybe like Google Image it or something, and you could find out maybe a more detailed drawing. But do you see how I can keep finding tangent lines, finding their zeros, finding the tangent line at that point, finding their zeros, and if I keep doing this, boom, 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 eventually I'm going to get, so the 0 of my line is the same thing as the 0 of the function. Okay, so here's what Newton's method says again. Take a guess. We're going to guess 3. Find the tangent line at 3. Find the x-intercept of the tangent line. And then start all over. Okay? So let's say we guess. Let's guess 3. So our first guess is x equals 3. Okay, and I'm going to take you through this, and then I'm going to kind of show you the pattern. Okay, so we're going to guess 3. Well, what's the slope at 3? Well, let's be clear. If this is our function, then we also know that the derivative, y prime, is equal to 2x. So at 3, I know I have x is 3, and I know I have a slope of 6. And when x is 3, I have a y value of 4. Okay, so then I can write the equation of that tangent line. Y minus 4 equals 6 times x minus 3. Okay, and what am I going to do here? This is the equation of the blue line. And I want to find the 0, meaning the root of the blue line. The blue line's root is when y equals to 0. So I'm going to plug 0 in for y, and I'm going to solve for my new x value. This new x value we'll call x2, will then be your second guess. So this would be, how would you solve this? Well, you could divide by 6. And then you could add 3 over. So it would be 3 minus 4/6 equals x2. And again, that's going to be 2.33 repeating, or 7/3. That's your new guess. Okay, and you start all over with that new guess. So you guess 7/3. And at 7/3, you'd find the tangent line at 7/3. So if x is 7/3, then the slope is going to be 2x. So 2 times that is just 14/3. And if we know that, then we also need to find the y value. Okay, this is going to get a little messy because this is going to be x squared. So this is 49 49 ninths minus 5. 49 ninths minus 5. Oh, what is that? Just 4 ninths then? Yeah. 4 ninths. And then we do the whole same thing again. Y minus 4 ninths equals 14 thirds times x minus 7 thirds. And we'd solve for this x value when y equals 0, right? We're going to let y equal 0 because we're going to find the 0 of that. So we'd let y equal 0 and we'd solve for this x. And it's going to get messier and messier and messier. Okay, so we could keep doing that. But really, what are you doing? And again, now we're going to take you to the formula. Again, if you just looked up Newton's method, this is probably the first thing that's going to come up. And I just wanted to show you what we're doing here. Guess, find the slope, find the y value, find the tangent line. Find the 0 of that tangent line. Finding the 0 of the tangent line is letting y equal into 0 and finding x. Find the x value, start all over and do another iteration. If you keep doing more and more iterations, you keep getting closer. But what are you doing? You're always just taking a line. And I'm just going to write it out in an algebra way, right, using like kind of point slope. You have a y1, you have an x1, and an m, right? X, y, m. X, y, m. And you're solving for x2. That's what you're solving for. You're finding the next guess, and you're making that 0. So how would you do that in the abstract? Well, you would just divide by m, and then that would equal x2 minus x1, and then you add over the x1. So then x1 minus y1 over m equals x2. Okay, I'm going to rearrange this. This is what it said. If you want to find x2, just take x1 minus y1 over m, and that m is specific. And here's the calculus version of that. If you want to find x2, just take x1, subtract f of x1 over f prime of x1. And that's probably what you would see if you looked it up. And again, I'm just changing what y1 is. What is y1? It's the y value at x1. Well, that is what f of x1 is. What's m? M is the slope at x1. Well, that's just f prime. So you'd see this. And you wouldn't have to go through this whole process of even finding it. You would just type it in. You literally would just, on your calculator, take your first guess and type in 3 minus the function's value at 3. Well, what's the function's value? That's just slapping in there. So 3 minus 4 over f prime at 3. Well, f prime of 3 is 6. Boom. Type that in. It's going to give you an answer. And that answer would just end up being 2.33, just like we said. Then you bust out your calculator. Choom. Type it in again, except you don't even have to do anything. This is still in your second answer. So on like a TI-83, you just hit second answer minus second answer squared minus 5, divide by 2 times second answer. Because you're just taking this and you're making your new x value. Well, your new x value is just the x value minus the x value squared minus 5, divided by 2 times the new answer. And hit enter again, and it's going to give you x3. And x3 is going to be 47 over 21. And then use that real quick. Again, don't type anything out. Just 47 over 21 minus 47 over 21 squared minus 5 divided by 2 times 47 over 21 and give you x4. And if you keep going, this one's going to be like 2207 over 987. And then if you think about the decimal there, it's 2.23607. And if you type in the square root of 5, they will be identical all the way through 5 decimal spots. That's pretty significant, meaning I used calculus, no calculator. I could have done all these fractions by hand if I wanted to, and I evaluated the square root of 5 up to 5 decimal spots just by using tangent lines and zeros. And so the beauty of this is a numerical method. And by brute force, I can use a numerical method and evaluate the square root of 5. And I could do this one just as well. This would end up being the cube root of 2. all I got to do is use this as my function, and then the derivative would be 3x squared. And I would do the same process, and I would go straight to here. I'd pick a guess. I don't know, guess 2, guess 1.5. Doesn't matter. I mean, what cubed minus 2? Well, it's the cube root of 2. Well, what is that? I don't know. 1.4, 1.2. I honestly don't know. I don't have my calculator in front of me, but I could guess 1.5, and then I could bust this up. Okay, one quick little idea. What are issues that could pop up? What issues can you have? Well, first of all, you can have multiple roots. And then you have to pick, your guess has to be close enough to the one you want to find. Certainly there were 2 roots here. If I would have guessed -4 or something, I would have went over here and got tangent lines, and I would have got closer and closer. So I picked some x value here, I would have gotten closer and closer to that root. So if you have some cubic function, or you have some sine function, it's got a whole bunch of roots, you have to be aware that there are going to be multiple roots, and you want to start closer to the one you want to find. Okay? What would happen if you were silly enough to pick where the derivative was equal to 0? Well, if you pick that point, it's going to be a problem. Your calculator's not going to like it because you're going to try to divide by 0. So that's an issue. And also, there are going to be values and times when the derivative doesn't exist at a point. And there are also going to be some issues. Okay? But the majority of time, you start talking about polynomials, this doesn't happen, and just don't pick the guess where the derivative is equal to 0, because if you picked right here, nothing's going to happen, right? You can't find the root of that tangent line. Okay, so the Newton's method is a numerical method in order to approximate roots, approximate square roots, and certainly it's got other options, but those are kind of the classic 2 examples to kind of look at.